Almost every review I see of a third-person 3D game complains about the camera failing in some way or the other. This video demonstrates the visual implementation of the two most important techniques needed in fixing the cameras of those games. This is only a proof of concept built in Blender, but illustrates how inexpensive these two techniques are in terms of computing load, and how elegantly they convey to the player relative positional information about how objects and surfaces relate to the avatar. I've talked extensively about how both of these techniques work in previous videos over the last couple of years, but this video is the first active real-time integration of these processes, and I'll continue to work towards learning how to implement them into a game engine in the years to come. On their own, either of these procedures aren't much different from many common practices already ubiquitous, but applying them in conjunction with each other in this specific way allows for a solution that is, as far as I've yet seen, uniquely effective in creating a lens that would allow for a logically concise view of the game world regardless of where the camera is viewing it from. The ubiquity of the practices has an added benefit of potentially allowing this fix to be easily implemented into any game that would benefit from it, either new or old. The first technique uses a piece of geometry that's only opaque where it can't be seen from the avatar's perspective, and thus anything in the background of the game view that is further from the camera than the avatar cannot be seen from the perspective of an out-of-bounds camera except through the windowed lens radiating from the location occupied by the avatar itself. The second technique is the patterned mapping of a partially transparent texture mask to the back faces of any collision-mapped geometry in the scene, so when the camera goes out of bounds or inside of an object, it visualizes the shape of the surface that the avatar has the potential to collide with when the avatar is moving in the camera's general direction. Neither technique is perfectly visualized here due to my own and my computer's current technical limitations, but I think they are sufficient as a proof and already better than the current standard both interactively and graphically. I've already addressed in past videos many methods to more dynamically optimize the ways this system can meet the circumstantial aesthetic qualities that different titles might arbitrarily demand, but even at its base level of implementation, there are some significant things that would be different about a fully successful version of Cammapper than what is on display. Obviously, the strange black dot that keeps appearing in the foreground wouldn't be there. It's an artifact from the ray emitting technique I used to occlude the outer regions of the background veiling object, which in this instance uses the scene's light source as the ray emitter, creating a value threshold flaw when the light gets too close to the surface. In the final form, the rays would emit from just above the head of the avatar. There are more issues still on display here, but I want to move on to the backface dots. Currently, I have them mapped as a texture to the backface surfaces that make up the scene's environment, but ideally the array would be a consistent wrap that perspectively isolates along the z-axis, which would eliminate those awkward seams seen at surface angle transitions, and each individual dot would uniformly shrink in size as they get closer to the camera. I don't have a visual representation for this, but maybe seeing it as an opacity transition might illuminate some of the effect. Another option is to billboard each dot while also scaling to camera proximity, which I clumsily attempt to show as a result here. It should also be pointed out that the use of dots is arbitrary, and there are a lot of examples wherein the use of symbol arrays could be effective in relaying what status change would be inflicted upon the avatar should it come in contact with the represented surface. Some people watching this with some technical knowledge of the issue might be thinking that what I'm proposing as a catch-all solution fails to account for the geometric complexities of modern game surfaces, which are invariably comprised of many subsurface layers, objects that are staged out of bounds, and wild amounts of aggregate billboarded textures. The first two of these issues are easily accounted for by inverting the surface render priorities in any space that is inaccessible to the avatar along the direction of view, thus automatically only rendering the back faces of surfaces that are directly exposed to accessible play space, and calling any geometry that exists behind them from the avatar's perspective. As for any rampant aggregate grass and the like, my past videos detail the use of automatic transparency gradients applied with regard to the relative angle and proximity to surfaces that are being backface mapped. This in conjunction with the now standard culling transition that invariably remove foreground objects with increasing effect as they get closer to the camera, ensure that aggregate graphics won't show unfinished edges or clip awkwardly through their once opaque faces when seen from the other side. In the mid-90s, the transition into 3D gaming forced a decision to be made as to what 3D camera systems would be installed as the standard practices. The solution that won was one in which the camera was deployed as a collidable object and was forced to zoom inwards in order to avoid going into most spaces that the avatar itself was restricted from occupying. But a few games, Mega Man Legends probably being the most notable of which, took an alternative route that allowed the camera to move freely through barriers while calling the back faces of their related geometry so as to keep an open view of the avatar's perspective, a no-forced zooming approach. This latter solution has since been universally seen as broken due to it allowing the player to peek behind the curtain of the game world stage, removing conceptual graphic immersion in the process. But I'd argue that the frustration that comes from the forced zooming method is even more immersion breaking, and that we, as consumers and designers, have gotten this wrong since that initial mid-90s decision was made. But if the idea of a game allowing the player to see it for what it is going to be a non-starter, then Cammapper allows for the best of both worlds by systematically putting blinders on the unsightly things that are lurking behind the scenes while never forcing the player to wrestle with an uncooperative camera angle.